All right, so we're looking at LSAT, score for applicants to a particular law school. They tell us that the mean is 650 with a standard deviation of 45. Suppose that only applicants with scores above 700 are considered. All right, so it's kind of a strange twist on it, but we can look at this as a conditional. So it's really the percentage of applicants considered to have a score below 740. It would be probability that your score, we'll let X be the score. The score is less than 740 given that it's already above 700. So it's kind of like looking at it from the perspective of if you're in the 700 category already, what would be the probability that you had a score that's less than 740? All right, so we can figure out each one individually. So probability that X is greater than 700. So that would be a norm CDF. We do norm CDF range if you want. All right, so let me bring that up. Oh, I already had it. Norm CDF range. Low bound 700, upper bound something big. Mean standard deviation. So we're talking about in the neighborhood of about 1.133. Now, within that set, I'm looking at the individuals who have a probability of being greater than 700 while also being less than 740. So another CDF range. This time just going 700 to 740. All right, that's about 0.11-ish. All right, so equals 0.11, I'll say 111. So we're looking at, if we're using the definition of conditional probability, again, probability of A given B is equal to probability of A and B over the probability of B. So in this case, I'm just kind of duplicate this and bring it down. I guess that's where it's going. The AND part is what we figured out here. So that's 0.111. And the given part is what we figured out earlier on, 133. So that's 0.111 divided by 0.133. And we're talking about something in the neighborhood of 0.83. All right. So that's kind of tricky. I don't like how these two choices are so close to one another because, again, if you're using a table approach versus a calculator approach, you should get something in the neighborhood of 0.83, but I don't like how it could be, like that gray area. Like, is it close enough to the 82.9? As it turns out, it is. And the one thing about these older practice exams is that they do have a lot of those decimal inconsistencies just because they were using a different approach. All right, number 32. If all other variables remain constant, which of the following will increase the power of a hypothesis test? All right. So increasing the sample size is one option, increasing the significance level, and increasing the probability of a type 2 error. All right. It's going to be choices 1 and 2. Really, honestly, for nothing more than that is what we define as increasing the power of a hypothesis test. You increase the sample size and you increase the significance level. All right. So that's more of a definition. I mean, there's theory behind it, but in crunch time now. So number 33, a researcher planning a survey of school principals in a particular state has lists of school principals employed in each of the 125 school districts. The procedure is to obtain a simple random sample of procedures from each of the school districts, and rather than grouping all the lists together, and obtaining a sample from the entire group, which I would think would be a simple random sample. Let's see what the conclusion would be. The procedure is to get a random sample of principals from each of the school districts and then put them all together, I guess. That sounds like it's stratified, which may give comparative information. I mean, they're giving extra details in it, but that's what a stratified random sample does. It takes smaller samples from each strata and then groups them all together. And it's definitely not systematic. Systematic, so C, would have been something like you line people up and you take every fifth person. Cluster sample would have been if I took all the principals from one of the 125 school districts. Definitely not simple. And proportional sampling based on the size of the districts, they didn't mention anything like that. 34, simple random sample is defined by, we got a method of selection, we got examination of the outcome. No sampling technique involves examining the outcome. So definitely not both of the above. How representative the sample is of the population, that's actually the opposite of what a simple random sample does. It's completely unbiased, so it doesn't care if the characteristics of the entire population are represented. It's just going to take the first n number of people out of a hat and make them part of the sample. So that wouldn't work. The size of the sample versus the size of the population. No. Right? What's the difference between taking 30 people in a simple random sample versus taking 50 people? Right? It's really not telling us anything about the population size or any kind of proportional relationship, so that's not a thing. The simplest one ended up being the correct one. It is a method of selection, or the method of selection. And that method is putting all the names of the individuals in a hat and randomly selecting n number of people. All right. Changing from a 90% confidence interval estimate for a population proportion to a 99% confidence interval estimate with all other things being equal. It's asking us what's going to happen to the interval size. So, or at least it seems that way. So increases the interval size by 9%, decreases it by 9%, increases it by 57%, decreases it by 57%. Well, it's a matter of area. So it's a population proportion, so that's a Z interval. This corresponds with an alpha of 0.1, and this would be 0.01. Right. So our formula, p hat, give or take the z alpha over 2 times your standard error, which happens to be, in some cases, p hat, other cases just an ordinary p. It really, for the purposes of this problem, it's not going to matter. Right? So it said all other things being equal, so we leave this alone and this alone. The only thing we care about is the impact that this has on the give or take. Right? So z sub 0.10 over 2 versus z sub 0.01 over 2. So that's z sub 0.05 versus z sub 0.005. Using my norm CDF, in this case we have the area, so I want inverse norm. I put in 0.05 with the 0 and 1 as my mean and standard deviation parameters. So that's going to give me and there is the plus or minus component here. So give or take 1.645. And then I can update this, put in an extra 0, 2.576. All right. So we're going to get, if we need to figure out what the size relationship is going to be, it's going to be a proportional relationship. So what we can do is we can take our z sub 0.005 and divide it by, because we're going from 90 to 99, so divide that by whatever we got for z sub 0.05, which is 2.576, sorry, divided by 1.645, which is about 1.57. So in terms of a percent increase, that's 1 plus 0.57. So the 1 representing the original quantity, I'm going to think percent change. The 0.5 would be a 57% increase. So if it were negative, if it were 0.43, it would be 1 minus 0.57. That would be different. That would be a decrease. But in this case, it's an increase. Which of the following is true about a hypothesis test? Let's see. If there is sufficient evidence to reject the null hypothesis at the 10% level, there's sufficient evidence to reject it at the 0.05. Not necessarily. Because if you reject at the 0.05 level, maybe your p-value was 0.08, something in that neighborhood. That would reject for the 10%, but not the 5%, so that's out. Whether to use a one-sided or two-sided test is typically decided after the data are gathered. I don't love that statement they throw in typically. Really, you kind of go into a hypothesis test having some predetermined significance level. Like you want to prove within a reasonable degree of certainty. We don't, I mean, in the pure sense, we don't decide after the fact what the alpha is going to be. Those are just for people who want to prove a point, and they're really just kind of forcing the data to prove their point. All right, so that's not the correct way of doing it, but that's what people do sometimes. Hypothesis tests you conducted at the 1% level, there's a 1% chance of rejecting the null hypothesis. All right, so that is not a true statement. The probability of a type 1 and type 2 error always equal 1? No, because it doesn't take into account all possible outcomes. Right? When we're talking about the different types of errors that you can make, you're mistakenly rejecting the null, mistakenly rejecting the alternative, but you could also correctly accept the null and correctly accept the alternative. Those are still probability values that would be accounted for. The power of a test concerns its ability to detect an alternative hypothesis. That's the true one. Right. And when they say detect, they're really just saying making it easier to reject the null hypothesis, which is in effect kind of associating with the alternative. Number 37. Population is normally distributed a mean of 25. Consider all samples of size 10, so small sample. All right. The variable says normally distributed, so we could go T or Z, but because of the small sample, I'm leaning towards T. But then also I see kind of tucked in here is a little S. All right, so that implies that sigma is unknown. So in addition to being a smaller sample size, we have an unknown sigma. So then I'm looking at a T distribution. Degrees of freedom in this type of distribution is n minus 1. 10 minus 1 will give me a 9. All right, so that's going to be choice C. All right, 38. Correlation of 0.6 indicates that the percentage of variation in y that is explained by the variation in x is how many times the percentage indicated by the correlation of 0.3. All right, so this is kind of a mean way of asking it. Percent of variation in one variable that's explained by the other is not r, it's actually r squared. All right, so they're asking us for the relationship between the two r squared values. All right, so this would be 0.36, and this would be an r squared of 0.09. All right, so 0.3 squared, 0.6 squared. All right, they're saying that this top correlation is how many times the correlation, the top, it's called coefficient of determination, but it's based off of, in many ways, whatever your correlation coefficient is. All right, so they're saying how many times is this compared to that? So that's just a 0.36 divided by 0.09, which is going to be equal to 4. All right, number 39, as reported in CNN or on CNN, in a May 1999 national poll, 43% of high school students expressed fear about going to school. Which of the following best describes what is meant by the poll having a margin of error of 5%? All right. Well, margin of error is really just your plus or minus. All right. So it's the give or take value. So sometimes the obvious answer is the correct one. So again, the poll was talking about the population proportion of high school students that express fear about going to school, right? So when we talk about a confidence interval, we're always investigating the true parameter, in this case, a proportion, right? The rest of them are just kind of red herrings, I guess. And then number 40, in a high school of 1,650 students, 132 of them have personal investments in the stock market. To estimate the total stock investment by students in this school, 2 plans were proposed. Plan 1 would sample 30 students at random, find a confidence interval estimate of their average investment, and then multiply both ends of this interval by 1650 to get an interval estimate of the total investment. I'm assuming for all students in the school, but you know. Plan 2 would have would sample 30 students at random from among the 132 who have investments in the stock market or in the market. Find a confidence interval estimate of their average investment, then multiply both ends by 132 to get an interval estimate of the total investment. I would assume, again, just applying to the 132. What's a better plan for estimating total stock market investment by students at this school? So keep it simple, plan 1 or plan 2, really. But we can look at the other possibilities. Both plans use random samples and well, that doesn't make sense. Just because random samples doesn't mean, again, the outcome is not determined by the sampling technique. Right? The outcome is, it's a consequence of it, but it's not like, oh, well, if I use this sample technique, I guarantee that I get these outcomes. That's not how it works. Neither plan will give an accurate estimate. I mean, we're using confidence intervals, so accuracy is in the eye of the beholder. So I don't know that makes much sense. Resulting data must be seen to evaluate which is the better plan. Not necessarily. The plans come before the outcome. It's another ends justifies the means idea. So now we're back down to plan 1 versus plan 2. Right? We're looking at it with I would lean towards Plan 2, and that's what I'm going to select. But in the high school of 1,650 students, 132 have personal investments in the stock market. That's a key component. You're already looking at such a small sample of the population. I'm going to select in Plan 1 30 students at random, all right, from the 1650. And then apply what we get there to all 1650 students. That doesn't seem like it would be the most appropriate way of handling it, because in theory, I could select 30 of the many students who do not have personal investments in the stock market. All right. So I'm going to get a widely varied set of outcomes. It could be possible that I get out of the 1650, 30 students who invest the most, and that would skew everything in that direction. Right, the likelihood that I would get a representative sample from the 1650 that would give me a true indicator, maybe a few that don't invest at all and a few that invest a lot and some people in the middle, that's probably not, regardless of how I do it, I'm probably not going to get something as accurate as I want it to be. Now, in the case of Plan 2, which is the one I was leaning towards, we're taking a sample of students who do invest from the 132 who invest. Then I get their average investment and then multiply the interval by 132 so that I'm broadcasting my sample findings out to that smaller subpopulation. So instead of all 1650, you realize, well, this doesn't really only apply to those individuals. It only really applies to the 132. So let's draw our conclusions and apply it to the 132. So we're going to get a distribution of data that's related to just the individuals who invest in the stock market. So that's why I would select choice B.